Hello class, and thank you for watching 3.1 Functions and Function Notation. In this section, we're going to discuss what a function is. We'll then go into how to evaluate functions using function notation, and then ultimately determine how to classify a function into one-to-one. Now for today's homework, it's only going to be about functions and determining if a relationship can be classified as a function. So let's begin by first reviewing what a relation is. A relation is a correspondence of a set of ordered pairs. The set of all first components of the ordered pair is referred to as the domain of the relation, and the set of all second components is referred to as the range of the relation. Now, normally we think about this as an ordered pair, as this value of x and y, but it could be anything right there, anything that we're pairing again up together. Now, there's specific relations that can be classified as a function. Now, a function is a relation in which there's a correspondence from the first set, again, the domain, to the second set, to the range, such that each element in the domain corresponds to exactly one element in the range. In Algebra 1, and again, the first time you were introduced to this, that concept was simply explained as your x values, or your first component, your domain, cannot repeat. So as long as your x values don't repeat, then the relation can be classified as a function. So for example, let's look at example 1 here. To determine if this relation is a function, well, we look at the domain here, which are the values 1, 3, 6, and 5, first of all, and the range are the values 2, 4, 6, and 8. This relation is in fact a function because the elements in the first components correspond only to one element in the second component to the range. So like the number 1 corresponds only to the number 2. It's only paired up with 2. 3 is only paired up with 4. 6 paired up to itself. And 5, it's paired up to the number 8. So this relationship between the domain and the range has this correspondence where every element in the range is the result of only one element one element in the domain corresponds to only one element in the range. So in other words, our x values do not repeat, so this is going to be a function. So let's look at this example now. If we have right here is a mapping. Our domain obviously is identified as these 4 elements here. Our range are these 3 elements there. And let's make this into a set of ordered pairs. So the arrows indicate how the elements in the domain correspond to the elements in the range. So with the arrow, x1 is mapped to x2. So it corresponds to the y value of y2. x2 is mapped to y1. x3 is mapped up or paired up with y3. And x4 is mapped up with y2. So if you see again, every x value is mapped to only one element in the range, to only one y value. So because of this, this too is also an example of a function. Now let's come up with some non-example. Let's come up with some examples of relations that cannot be classified as a function. Well, if we look at example A, and we consider again the relation 1, 2, 3, 4, 6, 6, and 5, 8, I can add another ordered pair. Let's say we add 3 and the number 7. So 3 is being related to 7, but we also have here that 3 is also related to 4. So in this scenario here, this would not be a function because, in very simple terms, is because the x value of 3 is repeating again in this notation. So we're repeating again that value. Okay, it would still be a function if I change this number. If I change this number to the number 7, and I add another 8. Okay, this would still be a function if I do that, because these numbers, again, 7 is only corresponding to the value of 8. But as soon as I have the x value repeat, so let me put this at the 3 again, this would not be a function. Sorry, I didn't write the word not. Let me write the word not. So this would not be a function as a result. And the same thing again with the mapping. x1, x2, I'll just do x3, and we'll do y1, y2, and y3. I'm going to make this really simple, just do across. So this right here would still be an example of a mapping, because x1 is only paired up with y1, the same thing with x2 and x3. It's only going to, again, be mapped to one of them. But as soon as I get an extra arrow from one of the elements in the domain to another element in the range, this is going to prevent it from being a function anymore, because we see right here that x1 is mapped and paired up with y1, but also with y2. So you can see again that the x values are repeating, so this again would not be a function as a result. Let's now talk about equations. Now, not all equations with variables of x and y define functions. Now, if an equation is solved for the variable y, so if you solve an equation for the y, and more than one value of y can be defined for a given x, meaning that y is equal to a possibility of a positive and a negative value, then the equation does not define y as a function of x. So let's look at examples of that. How can we solve it? And let's talk about the difference of when we're going to get the scenario that when we solve an equation, we get the possibility of getting both a positive and negative solution for that value of y. Well, if we look at the first example, example 2a, we have here that x to the second power plus y equals to 4. So to solve this equation, we're going to transpose the x and move the x to the other side, making it a positive x squared to a negative x squared. So we have here that y will equal to 4 minus x squared. And you'll notice again that this is the only possibility. We do not end up with the possibility of doing a positive or negative value of this thing. So this right here is going to be, let me write it underneath. This is going to be a function, okay? Now look, let's see if we could pick up on the pattern. Let's say I have this equation instead. Let me zoom out a little bit. Okay, let's say I have this equation instead, x squared plus y to the third power equals to 4. Well, to solve this equation, I transpose the exact same way. I'm going to move the x to this side of the equation, and we end up with y to the third power is equal to 4 minus x squared. Now, in this situation here, the way to solve this equation, because we have this power of 3, is to take the third root. So I'm going to take the third root. Let me get my marker instead. The third root of y. And of course, the general rule when it comes to equations is whatever I do to one side, I do to the other. So I'm going to take the third root also to the right side. That way I can solve this equation and again eliminate these two things. These are inverse operations. And I get that y is equal to the third root of y minus x squared. So again, I do not get the possibility of both a positive and negative value there. So this equation is also going to be a function. Now, compare that to example B over here on the right. In order to solve this equation, I transpose again my x term just like before and moving over here making it negative x squared. So I have y squared equals to 4 minus x to the second power. Now, to solve this equation, just like the previous example, because I have a power, I get rid of the power by using the appropriate root. So I'm going to use an root of index 2. In other words, a square root. Now, however, because I'm using an even root, a square root, this is when I comes with the possibility of getting a possible positive or a negative value or negative answer when I do that right here. So when I take an even root to cancel out an even power, this is when this possibility of possibly ending up with a positive and negative number exists. So because here y has two possibilities, y can either equal to the positive square root of 4 minus x squared, or y can possibly be I forgot to put the negative sign, negative square root of 4 minus x squared. You'll notice that this is not going to be a function, because if I plug in, for example, the number 0, if I have x equal to 0, this equation right here on the left is going to give me a y value of positive 2. Plug in 0 right there, that's 0. 4 minus 0 is going to be 4, and the square root of 4 equals 2. But if I plug in that same 0 into this equation right here on the right, I still get the square root of 4, but because of this negative sign there, I get that the value of y will end up equaling to negative 2. So you see, 0 is paired up to positive 2, and 0 is paired up to negative 2. So this would not be a function. As a result, now if I compare that, let me do another equation, x squared plus y to the, let's say, 8th power is equal to 4. And I do the exact same first step, move this over here to solve this equation for y. I get y to the 8th power is equal to 4 minus x squared. So to get rid of this power, again, to get rid of any power, we always simply just take a root of that index. So here, I'm going to take a root of index 8. So not the square root, but the 8th root. And I'm going to do the exact same thing to the right side of the equation. Now again, because I'm taking an even root, this is going to obviously cancel out, and we're going to end up only with y. But on the right side, yet again, we're going to get this possibility of a positive and negative 8th root of 4 minus x squared. So again, we get this positive and negative results, meaning that if I plug in 0, 0 is going to be paired up with two possible values. We're going to be paired up with one possible y value, and 0 is also going to end up equaling to the negative of whatever that y value is. So we end up again with two output values, and our x-axis is essentially repeating. So yet again, this is not a function. Now, if you do enough of these, you'll pick up on the pattern, and you'll end up seeing a shortcut. That this again is going to result when our y value is raised to an even number. Anytime our y value is raised to an even number, then we're going to end up, when we solve for it, we're going to end up with this possibility of ending up with a positive and negative symbol for, again, our solution when we take, again, the appropriate root. So as a shortcut, if you see that y is raised to an even power, 2, 4, 6, 8, doesn't matter, then the equation does not define y as a function of x. So you can use that shortcut every single time and not have to worry about solving the equation and seeing if you end up with this possible plus and minus symbol when solving. Again, just to recap, that doesn't occur when we have to use a root of an odd power. Like the third root will not give us the possible value of positive and negative, and obviously the power of 1 doesn't even require that. But 5, if I take the fifth root, if this would have been the 5 instead, so let me zoom in here. Had this been x squared plus y to the 5th power is equal to 4, then the answer would be y would equal to the 5th root of 4 minus x squared simply. Okay, that's the only thing that changes. And because this root is a 5, we do not get that positive and negative value. So this would still yet again be an example of an equation that represents a function. So you can use that shortcut. And ultimately, we have the last way to verify if a relation is a function is if we use a graph. So using what's referred to as the vertical line test, if we can draw a vertical line which states that if any vertical line touches, intersects a graph in more than one point, then that graph, again, does not define y as a function of x. So if you're ever not clear on whether an equation is going to be a function or not, simply use any graphing utility and graph the relation and verify that you can draw a vertical line that will intersect the graph only one time and no more than one. So like in this example right here, this right here, it looks exact, well, not exactly, but it looks similar to example 2, to this one right here. So if I was to graph x squared plus y squared is equal to 4, it would draw me a picture very similar to this. It will be more of a perfect circle. This is not exactly a circle, but it would draw something again circular like this. And when I use the vertical line test and draw a vertical line, I can find a vertical line that intersects the relation more than once. So because of that, this would not be a function. So this is a very easy test again, probably the easiest way to verify if your relation is a function. If you could just simply find a way of graphing it and just using vertical lines, you can determine again if it's a function or not. Like in this example, this next example right here again would not be a function. Because if I draw a vertical line, I see that this vertical line intersects the relation more than once. So this is not a function either. And moving on to the third example, this would be an example of a function because if I draw a vertical line here, it only intersects the relation once. If I move that vertical line and move it over here, I'll notice that it only touches the relation only one time again. And if I move it to a different position, let's say here, again, it only touches the relation one time. So this would be an example of a function. And the same thing with the last one. The last one is also an example of a function. If I draw any vertical line, each vertical line only intersects the relation in one location, like this vertical line only intersects the relation there. This vertical line intersects the relation only there. And this vertical line intersects the relation only right there. So this would be a function. So as you see again, this is probably the easiest way to verify if a relation is a function, which you can use in scenarios like equations. Because of Desmos and a lot of graphing utilities, if you were just to simply graph your relation, look at the shape of the graph, you can then just apply the vertical line test to determine if said relation can be classified as a function or not. Well, that concludes the first part of our notes. So this is going to cover again assignment number 1. I'll post the next video will be over assignment number 2, but still again in this part, and you can find all of the notes again in the Google Classroom. Well, I appreciate you again watching, and like always, I hope you have a great day. Goodbye.